Good evening, everyone. My name is Rashumba Llewellyn, and I'd like to welcome you back to another Tech Talk in our series sponsored by Remake Labs. Today, we have the pleasure of welcoming Christopher Sweeten to give us a brief talk about AI integration with MCP. So, without further ado, I'd like to pass it over to you, Christopher.
Perfect. I would like to start by thanking Remake Labs for sponsoring this tech talk, and I would also like to thank Rashumba for the introduction. So today we'll be going over AI's integration with the Model Context Protocol, MCP. I'm Christopher Sweden, and let's jump into this discussion. So we'll be going over 4 key topics with key takeaways at the end. I want to walk you through the evolution of AI throughout history and what capabilities evolved to make MCP necessary. I want to dig deep into the bottlenecks for AI agent systems before MCP. I want to define more clearly what exactly the MCP is, and then demonstrate its usefulness with some examples. And you'll see throughout a number in the top right corner. That's going to indicate what topic we're discussing based on these right here. So the modern AI wave began around 2012 when AlexNet showed that deep neural networks could outperform humans in image recognition, launching what is known as the deep learning revolution. By the mid-2010s, architectures like ResNet enabled much deeper models, advancing vision and speech. Then, in 2017, the transformer architecture launched in the research paper, Attention is All You Need, which reshaped the field, allowing models to capture long-range language patterns efficiently and paving the way for large-scale pre-training. Within a year, models like BERT and GPT-2 could understand and generate language, marking the shift from recognition to reasoning, although they remained largely task-specific. So by 2020, GPT-3 and other foundational models demonstrated broader, more general intelligence across domains. Yet, while these systems could process information consistently, they lacked context and real-world integration. So to address this gap, engineers began enabling models to use tools and applications, setting the stage for today's modern agentic architectures. These are intelligent systems that don't just respond, but can plan, reason, and act within their own environments. With AI systems now integrating with tools and applications, there had to be a method for connecting them. So before the Model Context Protocol, each developer had to regenerate unique APIs with which they could provide this access and bridge these entities. However, for each new agent added to the ecosystem, this meant more boilerplate, more APIs, and another non-universal schema to be followed depending on the tool being accessed. Very quickly, this technology had run into a few key roadblocks. So first, each agent had to create its own API connection just to communicate with external tools and applications. This meant writing custom integration code, handling tokens, constructing HTTP requests, and parsing JSON responses manually for every single platform every single time. Second, there was no shared schema between these integrations. They each had their own formats and implementation. Applications like Slack have their own format, while interfacing with a database like SQL is completely different. Additionally, agents were siloed. They couldn't infer how to use new tools without being explicitly programmed for them, and the context was isolated within each integration. One agent's Slack message history, for example, couldn't be reused by another system connected to, let's say, GitHub or Gmail. This all equated to high maintenance and duplication. Every new agent or service had to reinvent the same boilerplate for API calls, error handling, and schema mapping, with security being reinvented for each and every system as well. This increased the chances for exploitation, and just one simple bug in an implementation of an API could bring down the entire chain. So that's why in November 2024, just a year ago this month, Anthropic developed the Model Context Protocol, or MCP, to help connect their Claude models to external systems. MCP created a universal language based on JSON RPC that lets any model discover and use tools through shared schemas. Instead of hard coding these APIs, agents could now simply ask what capabilities are available and call them safely and consistently. It's what finally allows AI systems to connect, collaborate, and share that much necessary context. If HTTP standardized the web, MCP standardized AI to tool communications, and according to Anthropic themselves, you should think of MCP like a USB-C port for AI applications. Just as a USB-C provides a standardized way to connect electronic devices, MCP provides a standardized way to connect AI applications to external systems. Now, a quick and easy way to think about MCP is actually by referring to its definition inherently in the name. The Model Context Protocol can very simply be inferred as a protocol for providing context to models. So inside of this protocol, the agent becomes the MCP client, and then there's an MCP server, which becomes the gateway for the business logic, acting almost like the middleman for connecting tools and invoking actions. Instead of defining the logic inside of the agents themselves, they actually don't need to know what that logic is. It doesn't matter to them. In this way, the MCP server is almost like a black box. From the agent's perspective, all they want to know is what capabilities the server exposes for their use. So under the hood, the Model Context Protocol runs entirely on JSON RPC, which is basically just a simple method call language written in JSON. Instead of using dozens of unique REST endpoints, every interaction can follow the same exact format: a method name, parameters, and an ID. When an agent connects to an MCP server, it can send these standardized messages to discover capabilities or to execute one. The MCP host handles all the logic internally and sends back a structured JSON result that matches a shared schema. This makes MCP extremely clean and predictable. Agents don't have to care how a tool works. They just send a JSON RPC message and get a typed response. It's what turns tool integration from a tangle of APIs into a single universal conversational protocol. And now that we know what the MCP is, that it functions using JSON RPC, and that it solves this universal problem for the agent ecosystem, let's actually take a look at how it works in practice step by step. So first, when an agent first connects to an MCP host or server, it doesn't know what tools are available yet. The very first message it needs to send is one asking for a tool list. This is the agent saying, tell me what abilities you can provide me to utilize. Next, the MCP server responds with a structured list of tools, maybe things like GitHub repo list or Slack message send or calendar events read. These are all methods that they can call. In this case, we can see that GitHub repos list is a tool method we can access. So we can see its description for what it accomplishes. We can see its input schema, which houses what arguments this tool takes and what those arguments are with a description. It also declares required arguments, outlining further for the agent what it needs to provide versus what is optional. And finally, it defines an output schema, detailing what object type the agent should expect as a response within its own set of properties, in this case being a name and URL string and a private Boolean. Now, the key idea here that I want all of you to take away is discoverability. The agent doesn't need to know the GitHub API ahead of time. It simply asks that it's available, and the MCP server tells it, along with the exact input-output schema it needs to follow every single time. This is the first major difference from the pre-MCP world. Agents don't have to be pre-programmed for every tool every single time. Once the agent has this schema, it can reason about what it needs to do next. If the schema says it needs a username string, the agent can verify it has that data or even ask the user for it. This step is important because the schema ensures type safety and clarity. The agent no longer guesses or improvises about API inputs. Everything is explicitly defined. This allows AI reasoning models like Claude or GPT to automatically plan multi-step actions using these precise data formats. So once the agent has validated these inputs, it's ready to make a call. And as we can see, GitHub repo list is available. So in this example, this is the agent saying, call the GitHub repos list capability and pass in that argument username, which was required. And in this case, we typed just in the string octocat. And the MCP server receives this message and takes care of all the heavy lifting. It might authenticate with GitHub, perform the query, and also format the results according to the output schema. The agent now has clean, structured data. No raw JSON, no parsing errors, no special case logic. It knows that data is in an array of repositories, just like the schema promised, and we can see that here. Step 5, this is where MCP really becomes powerful. Although being optional, imagine you had another agent, say one that posts updates to Slack, also connected to the same MCP host. When the first agent finishes its GitHub call, the MCP server can emit a context update. That context can now be reused by other agents without repeating the same API calls. The Slack agent might see this update and automatically decide to summarize these results or even post them in a chat channel. This shared context layer turns isolated actions into coordinated multi-agent workflows, all without needing that central orchestrator or hard-coded connections. So let's go through the full MCP flow. In summary, these are the steps of utilizing MCP. First, the agents discover all the available tools using the tools list query. Second, the MCP client validates these input schemas and plans actions based on what data it has and its target. Third, once it's decided on an action plan, it sends another request asking either the MCP server or host to perform and execute the tools requested. And fourth, the MCP server will do all the heavy lifting, like we said, and actually perform these operations, returning the structured results. Lastly, in a multi-agent system, it would have the option to share this context of its just completed actions and results to the MCP host, which could then be provided to all other agents in the ecosystem for use and insight. And this is actually where the key value is and where I think the future is heading. Now, opposed to the single agent MCP system I diagrammed earlier, there is real opportunity for scalability under this protocol. By introducing multiple agents and multiple servers, each with their own purpose, and by adding an additional host layer, like I had mentioned, it becomes even more interesting. Now, instead of clients interacting directly to servers, the host takes the requests and responds in exactly the same way with JSON RPC, except instead of performing the calls, it can proxy those requests and redirect them to their specific server with all the business logic. It also enables that optional fit step we just showed, allowing for context sharing and universality among all agents in the system. Once a request and response is sent back and forth, the host can store that and update all the other agents in the system. And in that agent ecosystem or that LLM system, context is the glue that holds the reasoning together. It ensures that insights from one task instantly inform the next, transforming disconnected actions into intelligent collaboration. Imagine again that my Slack agent couldn't take advantage of my other agent's GitHub method call. It would have to waste performance to do the call itself, or maybe even not even have the capacity to do that call. So let's look at some key takeaways here of MCP. MCP standardizes AI to tool communications. It replaces that one-off APIs with a universal schema-driven language based on JSON RPC. Agents gain dynamic interoperability, discovering, understanding, and invoking new tools without ever having to be rewritten. It enables sharing context, which connects everything. Results from one tool or agent can easily flow seamlessly into another. And MCP is scalable and modular by design. New agents and capabilities can be added instantly to a growing ecosystem at any time and have the same capabilities via the tool exposure and JSON RPC. And lastly, it's built for collaboration, enabling multi-agent systems that can reason, plan, act, and learn together across domains is the real key here, and where I think a lot of the performance and productivity comes from. The importance of MCP lies in this simplicity. It's what transforms isolated intelligence into an interconnected network of reasoning systems. Without it, our AI models would be isolated from the world with no way of communicating. We would lose productivity, we would lose performance, and we would lose scalability alike in almost every single way without MCP. And again, if HTTP standardized the web, you can think of MCP as standardizing how intelligence connects to the world. And then I just want to share my works cited. And then I want to give a huge thanks again for Remake Labs for sponsoring this Tech Talk. Thank you.
Thank you so much, Christopher, for that informative talk. And thank you, everyone else, for coming out tonight. We'll see you at the next one.